All right, section 4.3 video, part 2. So what we've done so far is we've talked about a logarithm. We talked about the difference between a common log and a natural log. We're going to mainly talk about common logs. We learned that every common log, the argument has to be positive. The base has to be positive. But the base has one extra stipulation in that it can't be 1. Now, I haven't shown you why they have to be positive yet, but I will in this video here. All right, then we also, right in the last video, we learned if I gave you a log equation with the answer, we learned how to convert it to exponent form. And then if I give you an exponent problem, we learned how to convert it to a log form of the equation. So converting back and forth. I told you you'll see the significance to that in the next section. Not the next video, but the next section. We'll get back to that a little bit later. Okay, now what I want to do in the first part of this video is I want us to answer some log problems mentally. I told you in the last video where I wanted you to be able to do some of these without a calculator. So let's do, and all of the, now I can't just give you any old problem because some logarithms there's decimal answers. So if I ask you to do it mentally, I'm going to have to do it where the answer is something you can figure out in your head. In other words, I can't give you one where the answer is 14.793. You're not going to be able to do that in your head. So all of these I'm about to give you, we're going to do in our head. All right, let's look at this one. The log of 100. All right, what's the base understood to be? Base 10. So here's what this is asking. What would the exponent, remember a logarithm, your answer is an exponent. What would the exponent on 10 have to be to get 100? So in other words, 10 to what power is 100? Well, of course, that'd be 2. So the log of 100, base 10, is 2. All right? Let's do this one. The log of 16, base 4. So this means if you take 4, what exponent would have to be on 4 to get 16? 4 to the second power. 4 times itself twice. Now, remember, your calculator would have worked this one. Your calculator would not have worked number 2. So if I ask you to do number 2, you're going to do the second example, you're going to have to do that one mentally. Because the calculator won't work that one because the calculator only operates in base 10. Same with this next example. So let's look at it. The log of 125 base 5. Now I told you I got to give you one that's workable. So 5 to what power is 125? 5 times 5 times 5. 3 times is 125. Okay, the log of 64. Base 8. So that means 8 to what power is 64? That's 2. Now, here's why the base is so important. So if you do the log of 64 base 8, you get 2. Because 8 times 8 is 64. But look at this one. The log of 64 base 2. So that means 2 to what power is going to give me 64? 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. Times 2 is 64. So 2 to the 6th power. Now, once again, let me say this again. I would not ask you to do this one mentally. You could do it with your calculator, but you can't do it mentally. Because 10 to what power is 64, that's not a whole number. 10 to the first is 10. 10 to the second is 100. So this one's not a whole number. Now, let me say again, it has an answer. The calculator will work that. If you take your calculator and punch it in, you get about 1.8, something like that. And you don't even have to write that one out. I just wanted to remind you that, not all of them are whole numbers. All right, let's go back and do some that are whole numbers. So the log of 81, base 3. That means 3 times itself. How many times is 81? 3 times itself 4 times. Now let's look at this one. The log of 1 over 25, base 5. So this means if you take 5 raised to what power would give you this? Well, 5 to the 2 power is 25. But what would you have to do to that exponent to get it to flip it? You'd have to make it negative. So in this case, the answer is not 2. It's negative 2 because you need that flipped. Okay? Now, write these next 3 down together. We're going to do all 3 of these at one time. All right, let's do this one. The log of 10. So what's the base? 10. So if you take 10 to what power would give you 10? Well, 10 to the first power. The log of 8, base 8. 8 to what power would give you 8? 1. The log of 13, base 13, would be 13 to what power gives you 13? It would be 1. So the answer to all 3 of these is just simply 1. This leads us to a definition, and it's simply this. Whenever you're taking the log of a number, if your argument and your base is the same number, the answer is always going to be what? 1. So, write this definition right here now. The log of b, base b, equal 1. All this simply means is anytime these 2 numbers are the same. So 7, 7, 50, 50, 2.3, 2.3, pi and pi. Anytime these 2 numbers are the same, the answer is always 1. Okay? Now, let's write these next 3 down. The log of 1, base 7. The log of 1, base 10. The log of 1, base 6. Now you say, hold up, Mr. Rainer, I thought you told me earlier that this could never be 1. I did not say that. I said your base can never be 1. I did not say your argument couldn't be. As a matter of fact, the only stipulation on your argument was it had to be positive. The stipulation on your base, there was 2 stipulations. It had to be positive and never 1. All right, so let's look at these. So let's see. 7 to what power is 1? 10 to what power is 1? 6 to what power is 1? If you'll remember in our first video, when we were reviewing over exponents, we did these 2 problems right here. And we said anything raised to the 0 power is equal to what? 1. Anything to the 0 exponent. So, what would the exponent have to be on 7 to get 1? 0. What would the exponent on 10 have to be to get 1? 0. What would exponent on 6 have to be to get 1? 0. So this means the log of 1, I don't care what the base is. You change this number many times you want to make it. The log of 1, any base, is always 0. That leads us to our second definition. The log of 1, I don't care what the base is. The log of 1, any base. You put 8, 15, 2/3. You can't put a negative number and you can't put 1. But any other number that's positive, and the answer to that is 0. The log of 1, any base, is 0. Now, you don't have to write these down. I just want to show you. You remember I told you earlier, this number right here cannot be negative? Let me show you why now. If I take the log of -9, base 3, here's what this means. 3 to what power will give you a negative number? Nothing. You can't take 3 to a power and get a negative answer. And you say, well, if you make that exponent negative. No, remember, if the exponent's negative, it flips the answer. It doesn't make it negative. So you can't take 3 to some power and ever be negative. That's why that number right there can never be negative. Same thing here. This one, and I've already told you this, you can punch this in with your, because this is base 10. If you punch this in with your calculator is going to say error. And the reason is you can't take 10 to some power and get a negative. So that's why your argument has to always be positive. Now, for the same reason, well, let me show you something else. Remember, I also told you it can't be 0. Here's why. If you take 5 to a power, what power would you have to raise 5 to get 0? That's not possible. You say, well, 0. No, 5 to the 0 power is 1. So that's why your argument has to be positive. It can't be 0 and it can't be negative. All right. For the same reason, your base can't be 0 or negative either. But what was the other stipulation on your base? Remember, the other stipulation was remember, this is why the argument has to be positive up here. Now, remember, the base right here has to be positive, but it can't be 1. I'm just going to show you why it can't be 1. If you let the base be 1, which I can't do, but if I let the base be 1, try to work this problem. If you take 1 to what power, what would you have to put the power of 1 to get 10? You can't. Because if you do a power of 1, it stays 1 the whole time. So that's why this is what it is. Now, at the end of the day, let me just say it one more time, and that's because I'm not going to try to trick you up with this. This is all you need to remember. Your argument has to always be positive, and it will be. Your base has to always be positive, but never 1. You just need to know those two stipulations. Okay. All right. Just a second here. All right, what we're about to do now is I'm about to give you 3 properties of logarithms. And you're not going to know why on earth I'm giving you these properties, and we're going to practice using these properties. And hopefully when we finish it, you will understand it, but you're still not going to know why I'm giving you these properties until we get into the next section. But it will make sense once we get there. So right now, don't try to figure out how it all fits. You just stay in the moment, listen to what I say, take the notes, and just practice what I need you to practice right here. All right. First of all, when I say 3 properties of logarithms, what do I mean by properties? A property is just simply things you can and can't do with logarithms. Let me give you a for instance. You don't have to write this down. We did this a while ago. Are these 2 problems right here, are they the same? No, they're not. And the reason is because there's some exponent properties that tells me how to do this. And you don't do this one the same way you do this one. It's different rules. So how you multiply with x's and how you do a power to a power is two completely different things. Same if I ask you to do this. When I add these two terms, I don't use the same rule that I do to multiply. That's two different rules. That's two different properties. If I do this one up here, you get 12x to the third. If you do this one, you get 35x to the sixth. And the reason is there is a rule for adding variable terms, and there's a rule for multiplying variable terms. And that's two completely different rules, two completely different properties. So what I'm about to do is I'm about to show you some things you can and can't do with properties of logarithms. So what I need you to do first is just copy the three properties down. Never mind how we're going to use these, just copy them down. All right, so let me give you the three properties. All right, so let's see, yes. All right, pause the video now and write these properties down. Okay, so I'm assuming that you've copied these three properties down. And in the next video, we're going to look at some examples on how to use these properties. And let me show you how these properties are going to be used. When you're using these properties, you can use them from left to right, or you can use them from right to left. It depends upon what you're trying to accomplish. Let me explain. Look at the equal sign right here. Look on the left side of the equal sign on all three of these properties. How many logs do you see? One log, one log, one log. Now look on the right side of the equal. Two logs, and still only one log here, but mainly these two. All right, why is this called the product property? The word product means multiply. So the log of A times B. So if you want to expand this, and that's the word you'll hear me use. If you want me to go from one logarithm to multiple logarithms, that's expanding it. Now, I know that it seems like it would be this. The log of A times B is the log of A times the log of B. But it's not times, is it? The log of A times B is the log of the first one plus the log of the second one. You said, now wait a minute. That's multiplying, but why are we adding over here? If you'll remember, what is a logarithm? The answer. It's an exponent. The word logarithm and the word exponent are synonymous to each other. Let's come back to this problem right here. Look at this one. What operation is right here? Multiply. But when you answer it, what do? You add these. So you're multiplying over here, but you're adding to get the answer. So you're multiplying in here, but you're adding when you separate it. So let me say it this way. The log of a product is equal to the sum of the two logs. The log of a product is equal to the sum of two logs. So the log of A times B is the log of the first one plus the log of the second one. This is what we call expanding it. Now, if you want to put it back together, the log of A plus the log of B, when you put it back together for one log, is the log of this one times this one. When you put it back together, when you go from two logs to one. Now, same thing here. The log of A divided by B. It seems like it would be the log of the top one divided by the log of the bottom one. But it doesn't work that way. The log of a fraction is equal to the log of the top one minus the log of the bottom one. So the log of a fraction is equal to the log of the top minus the log of the bottom. Now, let me show you again right quick why that works that way. Look at this problem right here. X to the 10th divided by x to the 3rd. You're dividing. What's the answer to this? X to the 7th. Where does the 7 come from? You subtract those two exponents. So the log of A divided by B is the log of the top one minus the log of the bottom one. Now the next property I'll talk about, and by the way, when you put this back together, the log of A minus the log of B, when you put it back together as one log, you divide these. So these properties can go two ways. Then the last one, if you take the log of something to a power, you can bring that power down front. The log of anything raised to a power, you can bring the power down front. So here's what we're going to do in the next video. I'm going to give you some examples and ask you to expand the one logarithm. So I'm going to give you one log and we're going to pull it apart. So we're going to be using the properties going this way. Then after we do 3 or 4 of those, I'm going to give you a problem where it's already expanded out and we're going to put it back together as one log. So we're going to go both ways with this. We'll do that in the next video.